Hi, so my name is Immanuel, and I'll be discussing transformer feed-forward layers, key value memories by Geva et al. So this paper represents a lot of the baselines in terms of the current knowledge of what we know for model editing, and it provides a lot of information in terms of how we currently think that the feed-forward layers are where facts are being held and how those are what are supposed to be edited when doing a model edit. So a recap on autoregressive architectures. So this graph, or this diagram, comes straight from Vasani et al. For attention is all you need. And just looking at this as a recap, we can see some information. For example, there's multi-head attention. There's the add-in norm causing the residual connections, and there's feed-forward layers. There's also some cross-attention between going from the input embeddings and being mixed with your output embeddings. And what's really interesting is most of the work that's being done right now is looking at the attention layers and how they're contributing into what's being predicted for your outputs, simply because they were the new revolution in how neural networks were formed. But within a language model like this, since 2/3 of the model's parameters are in fact within those feed forwards or your MLPs, it's important to also consider what effect that those have in terms of generating your outputs. So essentially, the work with Geva et al. Was proposing that memory is actually held within these feed-forward layers, similar to a key value store. So within these feed-forward layers, we would see keys that capture text patterns within your input and values that represent distributions over an output vocabulary. So all of these added up with your residual connections and all of your previous inputs are used to build the final prediction, right? So just to recap what a feed-forward layer is, where your input is given by x, we would see a matrix multiplication with a weight matrix added by a constant. You have a nonlinearity, typically it's ReLU or JLU, and then you apply another weight matrix plus a constant, right? So all of these weight matrices and constants are learned parameters while training your large language model. Instead, how we can look at it if we abstract it a little bit differently is here we can see that x is your input, and you're multiplying it by k, which can represent a weight matrix that represents a key instead. You apply your nonlinearity and you get an activation amount. This activation corresponds to a row or a column within your values, which is another weight matrix, which tells you information on which value that you want to retrieve from your V matrix, right? So one of the first things that Geva did in order to sort of prove this is looking at what keys capture, right? And looking at the feed-forward layer again, we would see your input as a single vector multiplied each time by a column within your keys transposed. So when you do this over and over, you get a single value for every single one of those columns. And if this is size, for example, I don't know, like 1024 or something, you would see 1024 different values after fx matrix multiplied by a key transpose. And what Geva did was select the top 25 inputs towards each activation. So we'll look at one of these squares, these red squares, look for the top 25 prompts that would activate this single column, right? And what they noticed was looking at, a random assortment of keys across different layers and different positions. Within the first few layers, you would see shallow patterns. For example, the prompts that were fed into the network all ended with the same suffix. For example, substitutes, substitutes, substitutes. When you go into the middle of the neural network, you would see shallow and semantic. So instead of just ending in base, it could also be bases, right? And later on we would see something that it's more semantic and it's not just representing a single word, but it's like a part of the relations. So here we would see named as one, also a part of, among the top 10. So we can see from this that those keys can represent not only just these, what the last input token that was fed into it is, but also some relationships from the input itself. So what was also noticed was shallow layers appeared more early. So those ones that just represent, those last tokens or the first tokens being a very specific word, and semantic layers where it's more on the prose and the syntax becomes much more prevalent as you go later into the network. So on top of this, Geva did some work in terms of determining the purpose of the values, right? So here we would see that after your nonlinear activation, you would have values like 0.2, 1.5, 0 for every single one of those keys, right? So what does V2 do to the value 1.5, right? So what the team did was essentially look at the top activation, grab the V2, and then put it through the embedding matrix and see what's the closest token that can be represented by this. And this was actually compared against the token of the neural network itself that was going to be outputted next. And we would see that in the first few layers, it's all like nonsense. It doesn't have any correspondence towards agreeing with the final token output of the entire neural network. But once you get into layers 11 to 16, you would see much more correspondence. And these numbers between 0.5% and 3.5% agreement doesn't seem that high. But when you look at like the entire size of the vocabulary, this is actually like, pretty decent proof that these outputs, at least the most significant one as deemed here if we're just doing Armax, indeed does tell you some information of what's going to be outputted, right? So this we can kind of infer that based off of this, where you've already done all the shallow work by layer 10 or so. So you've already done all of the matching by keys, and you're spitting out values, right? And here we would see that this is just increasing slowly and slowly because all of that shallow work is already done. So on top of that, there was some work instead of just looking at one of these values and then doing the embedding, doing the argmax, it would look at all of those values individually and see if any of those corresponded to the final token output, right? And the overwhelming majority of the layer predictions have no agreement with those value predictions of those the entire model. And it indicates that, in fact, when you're looking at the MLP, it might not be just looking at one of these and then comparing over and over. All of these are essentially like put into your X residual back into your input, right? And maybe those layer predictions are a composition of many values. So this represents it right here. Your input after the feed forward is essentially your input plus feed forward, right? Corresponding to what we know about residuals. And what we found was we looked at the percent of examples. So here we can see that instead of the values being like 0 to 3.5% or anything, these values ended up being much higher in terms of corresponding to the final output. So here, even by layer 3, you would see about 22% of the time you would be able to extract the final output just by the residual. And by layer 16, you would see that the residuals would be around 85% of corresponding to the final output. So we would look in terms of where there's been matches with the final output token. So here we can see that most of them correspond to, we can see a match in terms of residual, right? Sometimes you would see a composition where in these cases it would be both, when there would be no match whatsoever. But a very slight amount of the time you would see agreement where both the residual and the output prediction within the feed forward network would both tell you information about what the output token is. And when we're looking at just the feed forward network, we would almost see like zero possibilities where one of the outputs and when you embed it and then look at the token, where that would agree with the final output and the residual doesn't, right? So this just gives more evidence in that the residual is, the sum of its parts. The input prompt matters and the entirety of the feed forward network matters. So just to give a few conclusions, we can see that keys hold textual patterns in inputs. Values represent distributions over the output vocabulary. Feed forward networks are built as a composition of many of those values. And while feed forward networks give much information comes from the residual matrices that are being passed downstream. So information being held in layer 8, being passed over and over and over. And outputs of FFNs perhaps only refine the model's predictions at every single layer.